Hello and welcome back to Automata, Grammars, and Computability. Today we are at video 3, where we're going to talk about non-deterministic finite automata, and we will start to talk about DFA NFA conversion. That's probably going to go into a part 2 of the video. Okay, so before we do that, let's do a little bit of review. What does it mean for a finite automaton to accept an input? So let's remember what we learned about DFAs and then try to remember the definition of accepting an input. All right, so the definition is that a machine, finite automaton, accepts a string which looks like W is equal to W1, W2, up to Wn for each Wi in sigma if there is a sequence of states R0, R1, R2, up to Rn in Q, where R0 is equal to Q0, Ri is equal to delta of Ri minus 1, comma Wi, for 1 is less than or equal to I is less than or equal to n, and Rn is in F. So that was the specific definition. So remember, we're going to have words that are going to be in our language, and you can basically break it up into the letters of the alphabet. So that's what Wi in sigma represents. And then you just go through this machine where it gets fed through these states, which is what these R0 through Rn are. And assuming you start at the start state and you have a transition and you end up in one of the accepting states, you're good to go. It accepts the string. Good. The other review question I have for you is to remember the definition of a deterministic finite automata. What do each of the elements of the 5-tuple Q, sigma, delta, Q0, and F mean? Q is the finite set of states. Sigma is the finite set of alphabet symbols. Delta is the transition function, which goes from Q cross sigma to Q. Q0 is the start state, and F is the set of accept states. Right, so this was the precise mathematical definition of the DFA, or deterministic finite automata. By itself, it's a little bit unclear what's going on, which is why we've done some examples. And we actually drew out a particular DFA. So here I have at the bottom of the slide an example where there are some states. I have Q1, Q2, and Q3. And I'm going to go from, I can travel with the letters A and B. So A and B are my alphabet. So what we do in the DFA is we're going to start at the start state, which in this case is Q1. And we're going to basically eat one letter or character at a time. So, or a symbol, however you want to think about it, but you have a word and it's going to be taken in character by character. Each of these input symbols causes a state transition. So if I see the letter A and I'm at Q1, I'm going to go from Q1 to Q2. A transition function, delta, tells us what the next state is. And after all the input is consumed, the machine either accepts or rejects. It has to be in one of the F states for that to happen. So here, basically, we can write down completely things like delta Q1 and the letter A is going to be Q2. And similarly, let me see, I'm going to have Q2 and A, which is going to take me to the next state, Q3. These are just some examples. So I can write exactly what exactly those delta transitions are going to be. I want to look at this example in a little bit more depth and actually talk about what all the delta transitions are. In this case, the alphabet that I have is A and B, and I define delta on every letter and on every state. So I have Q1, Q2, and Q3. And I can say, okay, delta of Q1, A, is going to be Q2. And even though I only drew basically just like one arrow here, that also represents a transition for B. So here, I'm going to say, okay, cool. So delta of B, Q1 and B is going to be Q2 as well. And so on. So I recommend taking a moment to fill in this table. You can pause the video. Let me go ahead and fill the rest of it out for you. You can check your answer. Delta of A and Q2 goes to Q3. And delta of B and Q2 goes back to Q1. And Q3 should be defined on all the states, so it just ends up going back into itself. With the example of this DFA, at every state, we had a delta defined for that state Q and that letter A or B. So with deterministic finite automata, we have the property that at every state, there is an outbound arrow for every letter in the alphabet. In other words, an outbound arrow for every X in sigma. That also means that the state transition function delta, which goes from Q cross sigma to Q, is what's called a total function. A total function is defined on every input. And it means that every step of the DFA operation is completely determined by the current state and the next input symbol. Now what I want to do is look at an example of an NFA and write down what the transition function looks like for this NFA. So I have delta, I have three states, Q1, Q2, Q3, and my alphabet is 0 and 1, and I recommend you pause this video and try to fill it out yourself. And then I'll be back with the answer. Great, so let's take a look, and we'll start with delta with Q1 and 0. Okay, looking at Q1, I see that there's an arrow pointing back into it with 0, but also an arrow pointing out from Q1 to Q2 with 0. So that is a bit weird, but what I'd write in here, I guess, is the states it can go to are Q1 and Q2, or Q2. And then moving on, if I want to go Q1 and 1, well, that one looks normal as before. It just goes to Q2. Next, I'm going to look at Q2. And I'm going to say, okay, if it's a 0, then it goes to Q3. So that seems fine. But there is no arrow pointing out from Q2 that has a 1. So it's going to be a fail. So you may have written fail here. Actually, what I'm going to write is that it's the empty state, empty set. And then moving on, Q3 has an arrow pointing back to itself from 0. So Q3 goes to Q3. Otherwise, Q3 goes back to Q2 on 1. So that looks like what we've seen before. So the parts to recognize that are new here is the fact that I could go to multiple states, or I could go to no states from any of the other states. So the the transition function is looking a little bit different now than it did before. With that example in mind, let's talk about how non-deterministic finite automata differ from deterministic finite automata. So one of the first things we noticed was the fact that we had missing arrows. A state Q did not have an outbound arrow for some x and sigma, and what that meant was that the state machine fails on that input when in that state. So if there's a missing arrow, then the state machine fails on that input when in that state. The other thing that we noticed was that there could be more than one arrow with the same symbol where either one could be taken. And so the transition function is defined a little bit differently now. It's defined as delta going from Q cross sigma union epsilon to 2 to the Q, and it's now a partial function. So we already started seeing that it was going to 2 to the Q because we saw that you could go to a subset of the states. So I just want you to remember that 2 to the Q is a way to write the power set of Q. One thing that we have not seen yet, but I would like to point out, is that an arrow can actually have the empty string as a label. So epsilon is not, or like the empty, like just not having an element, is not an element of the alphabet. But you can draw an arrow from a state to another state that allows you to take the arrow without even consuming any input. So you don't have to actually read any letters to continue. Right? So with that in mind, let's look at another example that's a little bit more complicated and see how these steps, these elements of the non-deterministic finite automata appear. Great. So here's our example. And things to notice here are that I have the alphabet A and B. Q1 has arrows, 2 arrows going out from it on A. So it can either go to Q1 or Q2. From Q2, you can see that it has 2 arrows pointing out from it from being B. Q3 has an arrow just for A, but also for epsilon, so you can take it without consuming any input. And Q4 has no arrows on it at all. So this is a bit weird in terms of reality. I will point out that non-determinism doesn't necessarily correspond to a physical machine that we can build, but it is useful mathematically. So if we understand the parts of this, we will be able to describe what sorts of strings this non-deterministic finite automata will take. So let's look at some examples. Here are some examples of inputs that my machine can read, and I want you to pause the video and try to figure out, is it going to accept or reject these strings and why? So let's go ahead and walk through what's going to happen with my elements here. Looking at A, B, one of the possible routes that I can take is actually Q1 going to Q2 because that's A, then B. And then you're done, or so it seems, because you're in Q3 and you've eaten all of the letters, but you'll notice that because of the epsilon transition from Q3 to Q4, you can just go to Q4 without actually taking any letters. So it turns out that AB is going to give you an accept. Now, let's look at AA. So there's a couple of different ways I could do this. From AA, so I'm in Q1, and Q1 can either, go Q1 and, just keep reading Q1 in, or I can do Q1 and then Q2, at which point I would fail because I don't have any arrows out from Q2 for an A. Now I could keep reading in Q1, go to Q2 at the end, but neither of Q1 nor Q2 are accept states. So it doesn't matter what path I take, I'm not going to be able to get to Q4, so I'm going to reject it. And one thing you might notice here as a pattern is that there's this B in the center, so at least there has to be a B to go from Q2 to Q3 and get towards accepting. Great, so let's consider now ABA. Okay, so what are the possible directions I can take? Okay, going from Q1, if I stay in Q1, I would fail. But if I go from Q1 to Q2, okay, A, B, then I can take that final A and go from Q3 to Q4, and I can see that that path allows me to accept. The final example that I have is ABB. So let's see, I probably want to go from Q1 to Q2. That seems fine. I have a B, I can go to Q3, but at that point I have a B only, and I can't read it. So from Q3 I can't take any B transitions, and so there's no way to get to Q4, and I'm going to reject. And so we can see that with each of these steps, there are multiple paths that you can take. If at least one of the paths is accepting, then the whole thing will accept. Now with that in mind, let's look at the formal definition. A non-deterministic finite automaton, or NFA, is a 5-tuple, Q, sigma, delta, Q0, and F. And it turns out all of these are the same as the definition for DFA, except for delta. So please take a moment to fill in what each of these things mean, copying over what you have as notes from DFA. All right, let's go through it. Q stands for the finite set of states. Sigma is the finite set of alphabet symbols. Now, delta is a little bit different. Delta is the transition function, and it's now defined as delta goes from Q cross sigma union epsilon, going to 2 to the Q. Q0 is the start state, and F is the set of accept states. Let's look into the NFA properties a little bit more, just to make sure we get these points through. As before with DFAs, the language of the NFA is the set of strings that it accepts. And we know already that you can have multiple paths from each state. So you can have 0, 1, or more than 1. You can also have what are called epsilon transitions, which allow you to move without reading any of the letters of the input. Then, a string W is accepted by an NFA if, given the input W, there exists a sequence of valid transitions from the start state Q0 to at least one accept state. So the important thing to see here is that there has to be just one sequence that works. So a lot of times what you'll do if you're looking at an NFA and trying to decide whether it accepts a string or not is just sort of guess and go along and see what's going to happen. And then if you get to an ending point, you're good to go, you're happy. But if it rejects, of course, you have to check every state path that you can think of before you can conclude that it's actually not going to accept it. So just talking about having that at least one accept path, there are a couple of different ways that you can think about non-determinism. There's mathematical, which is you can think of it as a tree with branches. You accept if any of the branches leads to an accept state. So basically, you just check all the possibilities. You draw out a nice little tree that tells you what those are. Another way to do it is if it's a little bit magical, which at each point you're going to guess at each step which way to go. The machine is always going to make the right guess that leads to accepting if possible. And that's sort of what you do naturally if you're looking at a pretty small diagram because it's easy to see what those guesses are. So just talking about the tree, basically you can think of if you can't figure out what's going on with that NFA, you can draw out a whole diagram and come in here and say, look, from, I'm going to come in on state Q0, and then from Q0, I know I can go to Q1 or Q2 or Q3. Maybe that will take me to Q4, and I see I have an accept state. Things like that you can do. And I'm just putting in random stuff here. And if you see that one of those branches works, then you're good to go. And you can pretend, of course, that there's a little oracle that tells you that you can do that, right? So this is just to visualize one way of potentially drawing out your NFA states if you can't figure out whether a particular string accepts or not. To allow us to understand what this tree looks like a little bit more, I have here an example. So in this case, I have states that I've named A through F. And then my alphabet is 0, 1. And now what I want you to do is consider a string which is going to be 0, 1, 0, 1, 1, 0, 0, 0, and try to draw out a tree of what's going to happen at each possible step as you are reading the letters of this input. So I recommend, again, pausing the video and giving it a try. Let's go ahead and try to draw out a tree. Starting at the start state, that's A, and the first letter I'm going to read is going to be 0. And I can see here from A reading 0, I can either stay in A or go to B. The next letter that I'm going to read is 1. But from B, there's no way to read 1, so that's just going to lead to a fail. So that doesn't go anywhere. From there, though, from A, I can read a 1, and I can go either to A, again, or to D. And you'll notice now I've read 0 and 1. The next letter I'm going to be wanting to read is 0. And from D, I don't have the ability to do that. So again, I'm going to fail. Now, from A, I can go to either A or B, reading the next letter, which is 1. But again, from B, I can't read a 1, so I'm going to end up failing again. And then again, I now can go to either A or D. And at this point, actually, you can continue on the D path, which you couldn't before. You can either go to E, or, and I'll just draw this out for you, you can do B, C, F, F. And you're actually good. That's an accept state. So it does accept. But from the other direction, from A, I again have this choice of doing A or B. And this time from B, I can continue. B, C, F. So we're good there. And then from A, I can do A or B, which can go to C. And that ends, that's a fail. But from A, I can go again and continue reading the input, which is A or B, and those are, of course, also fails. So you'll see here that there are 2 ways to get to accepting, just reading through the letters, and therefore this string will be accepted. Now it's kind of a hassle, of course, to draw out this whole tree, but I hope it does illustrate what exactly that would look like, and then you know that your oracle, if you're magic, you can just follow along and find a path that works. The tree nodes in the previous example had at most 2 children at each step, but in general, a node in the tree can have up to q children, where q is the number of states. The fewest number of children you can have is 0, which basically corresponds to the empty set. So you'll see here that a node in the tree can have any subset of the q states as its children, which includes 0. So with that in mind, I think it's a good time to look at how power sets work and understand what it means to be a set of sets, at which point we can end this video and start next time with talking about the subset construction. So I'm just going to do 2 small power set examples for you here. Please give them a try. First, I have the power set of the empty set, and then I want the power set of the set Q0, Q1, and Q2. Please pause the video and give this a try. The power set of the empty set is the set that includes the empty set. And you'll notice here that the empty set has size 0, but the power set of the empty set has 1 element in it. This is very weird, but now we can have kind of this like higher level idea of sets where we have sets of sets. For Q0, Q1, and Q2, you should have gotten 8 elements. They are the empty set, Q0, Q1, Q2, which are all sets, Q0, Q1 as a set, Q1, Q2 as a set, and Q0, Q2 as a set, and Q0, Q1, Q2 as a set, the whole thing. And if I count across here, I should see 1, 2, 3, 4, 5, 6, 7, 8 sets, and I do, so it makes sense because I had 3 elements, and now I have 2 to the 3 elements in the power set. So it looks like everything works out. Because this previous automata only had for each node up to 2 children, the only subsets I really care about are the ones of at most size 2. So in this example, I'd like you to take the set A, B, C, D, E, and F and write down what all the subsets of size 2 are, and then also tell me how many there are. So please pause the video and give this a shot. So what I've gone ahead and done is basically just written out A 5 times, B 4 times, C 3 times, D 2 times, and E 1 time. And basically the way I'm thinking about this is, okay, like A is going to get paired up with everything it sees afterwards. So which is B, AB, AC, AD, AE, and AF. Now, B has already been paired up with A, so B is just going to be paired up from now on with everything that comes after it. BC, BD, BE, and BF. And similarly for C, it doesn't need to be paired up with A or B, so I have CD, CE, and CF. And D is going to get paired up with E and F, and the only thing that's remaining now is E and F. And if you count up here, I'll have 5 plus 4 plus 3 plus 2 plus 1. And that gives me 15 different possibilities. Right? So as you can see, even with 6 states, which is not really that many, even if I had only the subsets of up to size 2, I already have 15 different states. And that's not even including the fact that I can also have 1 child, and I can also have 0 children, which is what all these stars mean when I drew the tree, which is to say that it went to the empty state. So things are getting big real fast. So this concludes this particular video, and next time we're going to talk about subsets a little bit more. And with that, we will be able to talk about the subset construction, which shows you how to build from an NFA a DFA. And the weird thing here, the takeaway is that NFAs and DFAs are actually equivalent in what kinds of things they can express, which is very surprising. All right, that's it for now. Thank you for watching.